Our next speaker is Professor Navneeth. He will be talking about measuring neutrino-nucleus interaction using Annie.
Hi, good morning everyone, and thank you organizer for inviting me. And okay, so yesterday we had a few talks on collider experiments and also on dark matter experiment. Today I'm going to talk about a neutrino experiment, a small neutrino experiment called ANI. It stands for Accelerator Neutrino-Nucleus Interaction Experiment. So before I go into detail of the ANI, I just want to give you a few ideas about the long baseline neutrino experiment and why ANI is important for long baseline neutrino experiment. Okay, so the next generation neutrino experiment is basically designed for measuring the CP violation in the electronic sector, basically measuring this delta CP associated with the PMNS matrix. And where in the neutrino case, what we are doing is that we'll have long baseline neutrino experiment where we have a intense neutrino source, and we'll have a near detector and we'll have a far detector, and then we'll measure the neutrino flux in the near detector, and then we again measure the neutrino flux in the far detector, and just by comparing the neutrino energy spectrum in these two detectors, we will extract the neutrino oscillation parameter, and that is the general philosophy of any long baseline neutrino experiment. Okay, so DUNE is a experiment which is going to take data in early 2030s in Fermilab. So here the baseline, that means the distance between neutrino production and the far detector is around 1300 kilometer, and this will give enough room for having like this matter interactions, and that will allow us to calculate the mass hierarchies of neutrinos. And the main physics goal of this experiment is to measure the CP violation just by measuring, just by looking into whether neutrinos are oscillating in the same way as that of anti-neutrino. Just by measuring the difference, one can actually get the value for the delta CP. So I would also like to discuss one slide on the detector technology that DUNE is using, and this is a state-of-the-art liquid argon detectors. So the liquid argon detector, the way it works is that when the neutrino interacts, so this is the entire detector volume is filled with liquid argon, and the detector volume is under a potential. So whenever the neutrino comes in and interact with the liquid argon, basically argon, it ionizes the argon and it will produce electrons. Okay, and these electrons will drift under this electric field, and then on the wires we will collect the electrons, and then that that signal is then converted into hits, and then we can get a clear tracks of events. And this is an event display of an old liquid argon experiment called Argonaut, which was in the Fermilab. So you can clearly see the details of the topology, and this way the liquid argon detectors are very advanced detectors which can actually do particle separation in a clear way even by just looking into the event displays. Okay, so now again I am coming back to this general philosophy of this long baseline neutrino experiments. So you will have a near detector spectrum and you will have a far detector spectrum, and then you multiply this spectrum by this oscillation probability, and then you extract the neutrino oscillation parameters. So here you can see in the different colors that shows the neutrino oscillation probability, how it varies with the different values of this two parameter. One is sin square theta 13 and the other one is delta CP. Okay, so this will tell you that in order to measure this neutrino oscillation properly, you need to have a better understanding about the detector systematics, because you see that these curves are very close. Okay, in order to separate out and take the value from the experiment, you need to know detector systematics in a very good way. And now the neutrino physics has entered into the precision era. So this has one of the importance of the global neutrino community, measuring the neutrino, understanding the neutrino systematics, systematic associated with the neutrino. So here I think it comes the goal of ANI. So ANI is a small experiment. So this is, it stands for Accelerator Neutrino-Nucleus Interaction Experiment. So we are small collaborators of 45 people from 6 countries. We also joined recently in ANI, and so I'll briefly talk about what this experiment is going to do. As I mentioned in the previous slide, that the global neutrino community is interested in measuring the systematic uncertainty associated with the detector as well as like the nuclear interaction model, etc. So here you see this is the cross section of neutrino, which is measured as a function of energy, and you can see for the different channel, especially in the low energy we don't have data, but even if we measure, like even in the 1 GeV area, there is a large uncertainty in the neutrino cross section. Okay, and you can see these different colors represent the different channels, and you can see the line below which actually represent the energy range of the different experiment, and any energy range is basically from around 500 MeV to 1 GeV. So this is basically mostly quasi-elastic interaction as well as the resonance interaction. In quasi-elastic, is basically in a neutrino comes in and hit the nucleus, and it will produce a corresponding lepton. In this case it is muon, because we mostly produce the muon neutrinos, and then whatever like the nucleon is. And there are deep inelastic and resonance production. So deep inelastic we don't consider here. The energy is not that much to go into the deep inelastic scattering in this case. And there are this resonance interaction also, in which there will be an intermediate resonant particle will produce, and that eventually decays into pions or another nucleon. Okay, so this is an important task, to understand the neutrino nucleus interaction cross section very well, because this is one of the input that goes into measuring the energy spectrum when we do the oscillation analysis. So here again, so this is again the role of how Annie plays an important role here. Okay, so the knowledge of the neutrino-nucleus scattering cross section is again crucial for this global neutrino physics community, and we have to understand a little bit more about the nuclear structures. So if it is just a quasi-elastic neutrino interaction, then it is not a problem. So you basically neutrino comes and hit the nucleus, you get a lepton and a corresponding nucleus. But in the case, we know that the nuclear structure is not very simple, it is very complicated. So there could be many interaction can happen inside the nucleus. Okay, so for example, there are like interactions like charge exchange, and there will be a pi zero can emit, and there will be elastic scattering within the nucleons, and then there will be pi plus can produce, and there are like a pion production where extra pi plus and pion will be produced, and these all will actually will be coming into the final state. And if it is pion, it's not a problem. We can actually still discuss still look for that, because the pion will decay, and one can actually look for the signature of pion in the detector. But and also in the true CCQ there are no pions, it's just basically the lepton and the corresponding nucleon, and here you can calculate the energy of the interaction just by the two-body kinematics, and it's very straightforward. Okay, so this is how we reconstruct the neutrino energy in a quasi-elastic interactions. It's very straightforward. But what happens in reality is for example, in a true CCQ there are no neutrons. Okay, it's just like the lepton and the proton. Okay, but what happens in some cases here, suppose there is an extra interaction within the nucleus, suppose that it hits some nucleons, for example, it can actually hit a correlated pair of nucleons, and then a neutron can emit from that interaction. So what happens is that now all our detectors are made to measure the charged particle. There is no way one can actually measure the neutrons. Okay, so then what happens if you don't detect those neutrons? That will exactly mimic like a true CCQ event, true charge current event, and that will introduce bias in your reconstruction, and that will cause extra systematic uncertainties in your neutrino oscillation parameters. So for example, if there are, suppose there is no pions at the final state, but there are like 2p2h interaction. This is where a neutrino interacts with a correlated pair of nucleons, and then these two nucleons will emit from the nucleus, and there will be neutrons. Okay, that neutrons, if you don't detect, that will exactly look like a CCQ interaction. And there are again stuck pions. The pions can stuck inside the nucleus, that can also hit a neutron, and a neutron can emit from the nucleus. If you undetected, that will look like a CCQ event. So that can actually cause a lot of bias in the reconstruction if you don't identify these neutrons. So here actually here is where Annie comes into the picture. So these are the goals of Annie, and I will probably talk about a little bit about the detectors and how we do the measurement, etc. in the next few slides. But the primary goal is to measure the neutron, the neutrino-induced neutron yield in water because we are using water as a detecting medium. So I will talk about that in next slides. So what we are trying to do is that we'll measure the neutron production when the neutrino comes and hit the nucleus, and if there are like a neutron is producing, we will have an upgoing lepton which is muon. As a function of like the momentum of the muon, one can actually count how many neutrons are emitting from these reactions, and that can actually give you a plot where you will have a neutron number of neutron in x-axis, and then you will have a muon momentum as a function of muon momentum. Okay, so this is a small experiment, as I said, and so this small experiment can also, this is another goal of Annie, this can actually demonstrate new technology that will help for future physics. For example, since it is a new it's a small detector, whenever there is a new detector technology comes, if one wants to test that detector technology, one can actually bring it and put it in the Annie tank, and then you can do some measurement, and that can actually kind of validate your detector technology. Okay, that is the idea of like the Annie experiment. We did two such detector testing in Annie, and I will also briefly talk about that in the last few slides. And on top of measuring like the neutron multiplicity, Annie can also do cross-section measurement. And then the another thing that we can do is there is something called SBND, short baseline near detector, neutrino detector, which is actually a near detector in Fermilab, which actually built to measure, look for this sterile neutrino anomaly that people have seen in mini bone. Okay, so this SBND uses argon. So one can actually do a cross-section measurement both on water means oxygen, and in liquid argon, and that will be extremely helpful because dune is also going to be a liquid argon detector. So once you measure the cross-section of this neutrino with the even though energy will be different, but if you once you measure things in the liquid argon, that will give you some insight about the uncertainties in dune. Okay, and as I said, this can actually use to demonstrate new detector technology. So there are two detector technology that we have so far tested. One is called large area picosecond photo detectors. These are like MCP based photo detectors, and this has a very high, very good time resolution around the picoseconds. So I will talk a little bit about large area picosecond photo detector also in my in my last slides. And then there is another technology. This is called water-based liquid scintillator. So since Annie is like a water-based detector, mostly we are doing we are using this Cherenkov light to reconstruct the muon path and to understand the kinematics, but we won't get any scintillation light. And for getting the Cherenkov light, there is a threshold, right? But if you add liquid water-based liquid scintillator, that can also measure the scintillation light. In the case of a Cherenkov light, it is mostly forward going, and whereas the scintillation lights are isotropic, and we use this property to distinguish between the scintillation light and the Cherenkov light. That also I will discuss, and we have demonstrated that one in principle can use this water-based liquid scintillator for measuring scintillation light, and one can also use this directionality technique to separate out the scintillation light and the Cherenkov light. And again, so Annie will we will be taking data for at least for next 5 years, and this will be a platform for test any new detector R&D for the future large scale experiment. Okay, so now I'll come to this experimental setup. So we use neutrinos from the booster beam. It's like the small accelerator in the Fermilab. It's basically in the beginning of this 120 GeV protons, this proton will go into this booster neutrino, and booster neutrino basically will give you protons at the energy of 8 GeV, and that will actually hits in beryllium target and will produce all set of pions and kaons. And this is typically a neutrino beam is produced in any neutrino experiment, basically accelerator based neutrino experiment, and then this will produce all type of pions and kaons. This hadron production will happen here, and then you can also use a magnetic focusing cone, and depending on the polarity of the magnetic focusing cone, you can either choose pi plus or pi minus, and depending on that, one can actually choose whether you want to run it in neutrino mode or you want to run it in the anti-neutrino mode. And these two plots show the spectrum. One is for the neutrino beam, when one is for the neutrino mode, and the other one is for anti-neutrino mode, and you can also still see some. So mostly here the pions, when it decays, is mostly produce muon neutrinos, but there will be some contamination from electroneutrino from this cation decays that will be also present in the beam, but the beam composition, at least in the neutrino mode, it will be 93% of neutrino, and then there are the other component which is present in the beam. And this is the Annie detector. Okay, Annie detector, like it is 3 meter in diameter and 4 meter is the height, and this is the tank, and it's filled with water, and it's not just water. I'll talk about the main thing. So because we also added gadolinium in this water. Okay, the gadolinium help us to measure the neutron, because gadolinium neutron capture cross section is much higher than water's neutron capture cross section. So what happened is that, and there is also some front end anti-coincidence counter, so which basically emit all the particle which is coming from outside. We can tag them and we can actually emit them, avoid them. And in the tank, what happens is that when a neutrino interaction happens, if a muon produces, and if the muon energy is above the Cherenkov threshold, that will produce Cherenkov light, and we have placed this photomultiplier tube inside the detector, and this photomultiplier tube will read the Cherenkov light. And then suppose if there is a neutron also emitted in this process, okay, in ordinary detector you won't be able to measure it, but here what happens is that since there are gadolinium in this detector, this gadolinium will absorb this neutron, and then it will go to the excited state, and then the neutron will thermalize and capture inside the gadolinium, and that will emit a gamma ray, and this gamma ray one can actually capture inside the photomultiplier, inside the detector. So you will have a prompt light from this muon, and as well as also a delayed light from the neutron, and these two will confirm that there is a neutron also associated with this interaction. And this is a typical event display. These are the PMTs on the side wall, and this is up on the upside, and it's on the downside. And there is also muon range detector behind this detector. What happens is that if the muon is energetic enough, they will actually go to the MRD, which are basically plastic scintillator detectors, where you can actually track the muon, and this helps us to reconstruct where exactly this neutrino interaction happened inside the detector volume. And this is a few pictures of we are building this detector, and this is how it looks like before it actually covered with this vessel. And these are some clean room activities that we are doing, and we are also did some gadolinium compatible tests, because most of the detector, you have to make sure that all the components that we are putting into the detector are compatible with the gadolinium. So we have done that test also, and there are total 132 photomultiplier tubes, and these are the different type of photomultiplier tube that we uses in your detector, and it's not that important. Okay, so what happens once the BNB, that is the booster neutrino beam, which delivers the proton, and this is like the this actually come as a pulses, like the 1.6 microsecond is the width of the pulse, and it comes at in a frequency of 5 Hertz, and the mean energy of the neutrinos are around 700 MeV. Okay, so this is basically an table which actually describe how many events we are actually expecting in this detector for an year. Okay, so you can see that we can get all type of NC, CCN, CCQ and other type of events, and you can also see how many of the CC event will go into MRD, that is the back side of the detector, and you can see that NC events are mostly kind of longitudinally spread, and it will not go to the MRD. That's why the numbers of NC event, that the neutral current events which is entering into the MRDs, are very low. Okay, this is just like a statistics showing how many events that we are expecting per year. Okay, so now this is the structure of the BMP that actually this was done by some other experiment with the help of accelerator division. So this is like 1.6 microsecond wide, the beam, and then this is like the properties of the benches, 2 nanosecond width, and there will be 18 benches in this 1.6 microsecond. Okay. So first we have to do, what we have to do is that the neutrino beam is coming, and we need to make sure that in our detector we are seeing the signal, right, neutrino signal. So this is a typical PMT hits, which looks like in any detector, and you can clearly see that there is a 1.6 microsecond window above the background, and this will confirm that we are actually getting the neutrinos which is coming from the beam. Okay, this is a first step that we do to make sure that we are actually detecting the beam neutrinos in our detector. And what happens then, these are basically this neutrino event, and then if there are like an activities, neutron activities, then we will actually read out for another 70 microsecond, and that will help us to capture the neutron which is emitted from this reaction. Okay, so this is like we call the extended window. Okay, so if there is a neutron activity, we will just extend the readout window so that we will make sure that we get the neutron. And again, this is a neutrino candidate, and then what happened is that then we have to make sure that the neutron candidates are real neutron candidate. Okay, so then we did we measured this neutron capture time, and it basically follows an exponential loss, and we can see that okay, so here is the number. Okay, so the average cross section of like a gadolinium is for 49,000 bonds, whereas for the hydrogen it is 0.3 bonds, and you see that the neutron thermalization, that means the capture time, in gadolinium it is 30 microseconds, if it is in just hydrogen it is 200 microseconds. So you can see that it is actually reduced a lot if you add the gadolinium. So you can see, you can do an exponential fit and you can calculate this number, and we are getting around 29 from this fit, and that actually confirms that this is basically neutron. And this is basically some neutron events that we detected in this extended readout window, and this basically shows that there are neutrons, and we can actually detect these neutrons. And this plot is very preliminary, and you can see that there is a lot of mismatch between data and Monte Carlo, and we are still investigating that. So this is basically show the number of neutron and the x-axis, and you can see that most of them have one neutron, but you can see there are events which more number of neutrons in this particular plot, and you see that we have a low statistics, even we don't have this generated Monte Carlo for this number of events, and we are still investigating where this data Monte Carlo effects are coming from. We have some hints related with the detector geometry and etc. So we are actually looking into it, and we hope that it will improve in future. And I want to briefly talk about this detector R&D thing that we are doing in ANI. Okay, this is this LAPPDs. So these are like large area picosecond photo detectors. So this is like a photo multiplier too, but it has a very good high time resolution. So whenever there is a these are basically called a micro channel plate imaging photo detectors. Whenever there is a photon comes, this will actually go into this micro channel, and that will get actually amplified by the photo cathode material, and then you can actually read it out. And this is basically a 20 centimeter wide tile, and the good thing here is that the transit time spread, if you measure, this will be around picosecond order. So you can do a lot better physics, like if those physics you require like picosecond order resolution, one can actually do with the LAPPDs, whereas you cannot do that with the PMTs, because conventional PMT has a transit time spread of around nanosecond. So in that sense, LAPPDs are like a very promising detector technology, where one can actually use it for doing physics which requires much good time resolution. And you can also see that how LAPPD, the position resolution is also better, how LAPPD actually help us to improve the vertex resolution. So you can see that without the LAPPD, just by the PMT, this is the vertex resolution, it is around 38 centimeter. Once you use 5 LAPPD, you can see that resolution is coming down to around less than 10. Okay, and this is basically how it goes. It's a cumulative graph of the same thing. And this is the this we have done it in the last year, and the one thing about this LAPPD is that so you have to actually mount all the electronics behind the LAPPD. Okay, so you have to make sure that this entire electronics is waterproof. Okay, so you have to do a lot of R&D to make sure that this entire electronics is waterproof, and then you use like a slide to actually lower this detector system into the tank. Okay. And here also, currently we are using 3 LAPPD, and this is roughly the position of this LAPPD within our detector. And you can see we just confirm that we can actually see neutrinos from the beam, and this is like the world first measurement of accelerator neutrinos with using an LAPPD. And for these three LAPPD, you can see that we can clearly see the beam window. Okay. And the other detector technology that I just mentioned is water-based liquid scintillators. So liquid scintillators are helpful to measure the scintillation light coming out from the interaction. So scintillation lights, this is basically the total the WBLS curve, and you can see that the scintillation component and the Cherenkov component in blue and green. So this is what we observed. Okay, so we recently did a measurement with a water-based liquid scintillator in any detector. So this is what we observed. This is basically we are looking for the symmetry in the upstream and the downstream of the detector. And if you are not using a WBLS, you see that most of these hits are like this. But once you use the water-based liquid scintillator, you can clearly see a isotropic distribution of hits. And again, this is some parameter that one can actually use to separate out the Cherenkov light and the scintillation light. And again, this is a very preliminary thing, and we are still looking into the data carefully, and hopefully we'll able to come up with some other parameters which we can use to separate out the scintillation light and Cherenkov light. Okay, so this is actually, we have demonstrated the WBLS technology first time in a neutrino beam, and this paper has now out, and you can actually go and read this particular paper if you are interested in using any water-based liquid scintillator. Okay, so now with that I will conclude my talk. So Annie will assess this neutron multiplicity, and this will give you data to validate model describing the final stage. Okay, a lot of theoreticians are also interested in knowing the result from Annie, because they can also tune their model according to the data. Okay, and we have done a phase 1 measurement, which I didn't talk in this particular slide, where we are actually looking for the background. Okay, before we do the actual neutron capture measurement, we have to make sure that the environment is background free. So we have done a background measurement in phase 1, and I can show the result if you are interested, but not here. It's in the backup slide. And this data collection is in progress, so hopefully we'll have more data in the coming years, and that will give more hint about this neutron multiplicity. And Annie is the first neutrino detector that uses LAPPD to detect accelerator neutrinos. Okay. Additionally, we have also examined the capabilities of water-based liquid scintillators. So so we are actually taking more data, and hopefully there will be more result coming in the next few years. So stay tuned. Thank you.
Thank you. So any quick question?
Hi Navneeth, thanks for the very nice talk. So I have a question. So you must have the information of the angular distribution of the events, right? Because as shown by Minerva, that also plays a role in fine-tuning the neutrino generators, like Gibbu and other things. So
the angle actually goes here, right? I mean, so we know the Cherenkov angle. We can actually reconstruct this, for example.
No, I know the Cherenkov angle. I'm saying the angle of the outgoing lepton.
So one can, you can do that.
The sigma d omega.
Correct.
That has an input on the neutrino generator.
So that is actually difficult in Annie, because it's a small detector volume. So getting a better angular resolution in this small detector area, volume, is very different. The only thing that we can use to calculate the angle is just the MRD track, and you have to just back propagate the MRD track to calculate the theta, the kinematic variable theta. So I think in the case of Annie, it will be difficult. You need a little large volume detectors to measure it more accurately.
Okay, thanks. Thank you.
Hi. So I was curious about the LAPPD detectors. I think you had the figure on 21 or something. Yeah. So this middle picture, I can see some kind of detectors at some angle.
Yeah.
Is that so? What is that angle for? And
No, this is
what
just
is
like
that
these are like there are like these are micro channel plate detectors. So there are like microporous structures inside the detector. So this basically shows an incoming photon which actually hits in the within the, because these micro channel plates are actually covered with photo sensitive material. So this angle just basically show that this particle is actually going into the micro channel plate. There is nothing more about angle.
Not the angle of the red, which perhaps shows the photon going. The detector itself seems to have some things at an angle. Is that something I should?
Oh, this micro channel plate.
Yes. So why are they at an
So
angle
I think,
and not?
so I'm not sure, but I think the reason is that to make the acceptance bigger. So yeah, I don't know whether there is any other reason behind why these micro channels are slightly in an angled position. I have to check.
Yeah, hi Navneeth. If your proton pulse width is around 1.5 microseconds and neutron thermalization is around 30 microseconds, how do you tag the events?
No. So I think, okay, so this is basically the beam. Okay, once there is the beam, which is 1.6 microsecond, so we are done with the beam. Okay, so then what happens? Suppose that if there is within this beam, if we see some event in a tank, and then what we do is that we will actually extend our readout. Okay, because the neutron may be so once the neutrino hits the detector, it will produce the neutron, right? And then within this 2 microsecond window, if we see a neutron activity, we will extend our window for next 60 microsecond, and then we will look for neutrons in that next 60 microsecond window. That has nothing to do with the beam width. And then actually, if there is neutron, and then, of course this neutron will take 30 microsecond to thermalize, and then that actually we can actually capture by measuring the photons.
Yeah. So per beam you expect less than one neutrino event. Is that correct?
Yeah. In
okay.
per spill, that is true.
Okay.
Yeah, it's a near detector. You will get more statistics as compared to the far detector, but still it is per spill. Yeah, you can mostly expect. I think I have mentioned it somewhere here. Yeah, one per this many spill. 150 spill, yeah. So there is no pile up, or we don't have to worry about the reconstruction pile up.
How do you measure the neutrino beam composition? The beam composition, you said, okay, this fraction is new mu, this fraction is new electron. Okay, I mean.
This is actually okay. So one thing is that one can actually look.
Is it measured or calculated?
So one is actually, this is calculated like some hadron production model, and also there are in this decay pipe there are muon monitors as well as but I think that will actually measure the muon, not the muon neutron. Yeah, this is basically, this parameterization comes from the hadron production parameterization, and this is what is most of this Na69 MIPP experiment that they do measure it.
So for example, okay, if there is neutrons in the beam, okay, I mean, is there a measurement for that?
Not for the neutron, but neutrons will not reach here, right? That will basically probably absorb in this decay pipe, or before it reaches into the detector. That
there is no measurement anyway.
No, there is no measurement. But what we have done is in Annie, we have measured the beam correlated neutron background. So those neutrons are basically produced if the beam actually went and hit the upper part of the detector, and if it produces a neutron, that neutron can actually come into the detector. That we actually measured, and that background is basically less than 0.02 per meter cube per spill. Yeah. And this is actually we measured in Annie. That is the beam correlated neutron background, but that is not the beam, the neutrons in the beam. These are like the neutrons which is produced somehow from the beam, like maybe with some interaction with the wall or side of the detector, etc.
I mean, you have no way of measuring, for example, the vortex distribution.
What distribution?
Vortex distribution. Okay.
No. Vortex distribution of neutron we cannot measure in this detector.
I mean, that is an easy way of measuring the neutron contamination in the beam.
Correct. But yeah, we don't. Yeah. So in the beam, it's mostly all the other hadrons will get absorbed within the decay pipe, right? So I don't. But the contamination one can actually do measure. But I haven't seen any such measurement, measuring the contamination of like a neutron contamination of beam. I haven't seen such a thing, but I can look if there are some document related with that.
Okay, so let's thank the speaker once again.